Hello everyone, thanks for coming. I'm Xiaoyan Deng, a PhD student from Dr. Morgan Craig's lab. So today I'm gonna talk about one of my PhD projects that I'm currently working on. Predicting heterogeneous cellular immunological memory responses in COVID-19 using a virtual patient cohort. So firstly, I'm gonna give you a bit about the background. According to various studies, the COVID outcomes are quite diverse. Most infected people are experience asymptomatic or mild symptoms, including fever and cough. But severely infected people require hospitalization. So throughout the whole pandemic, a lot of efforts have been made to understand the mechanisms of the immune response to SARS-CoV-2 infection and try to investigate what caused severe COVID-19. Unlike antibodies, the cytotoxic T cells, the CD8 T cells, are the major component of the cellular immune response that can protect our body from the intracellular pathogens by killing infected cells. After a successful immune response to SARS-CoV-2 infection, some effective CD8 T cells remain in patient body and can convert and form an antigen-specific memory. A lot of studies shows this kind of memory can exist in humans' body for several months to decades after infection or vaccination. So next, I'm gonna show you the model schematic of the immune response to SARS-CoV-2 infection from our previous work. So this is our model. Our model is actually an extension of the SIV model. Susceptible lung epithelial cells get infected by free SARS-CoV-2 virus, and they end up dying lysis and create new virus. During infection, infected cells release type 1 interferon. This type 1 interferon can block viral replication inside the infected cells. So it actually inhibits the production of newly infected cells and induce the production of resistant cells. When inflammation gets higher, the neutrophils will be recruited to the system by the two cytokines IL-6 and GCSF. Neutrophils will cause the death of all cells, whether they are infected or healthy. Another component in our model is the differentiation pathway from monocyte to inflammatory macrophages. Monocytes are recruited by infected cells and GM-CSF from bone marrow, and they can differentiate into inflammatory macrophages according to the concentration of IL-6 and GM-CSF. Tissue-resident macrophages become anti-inflammatory macrophages through the interaction with infected cells and dead cells. Dead cells are removed by inflammatory macrophages and also cause their death. Lastly, we have the CD8 included in our model. Their recruitment is regulated by interferon, infected cells, and IL-6 concentrations. And CD8 T cells also induce the death of the infected cell. We also model the concentration of these four cytokines systematically, as well as their binding and unbinding kinetics. So this is our complete schematic of the immune response to SARS-CoV-2 infection. To model the immunological memory response, we extend our previous model by introducing the generation of two subsets of CD8 T cells, the effector CD8 T cells and memory CD8 T cells. And we consider primary infection and reinfection separately because the generation process are different. For simplicity, we'll assume that this differentiation process is a linear. So in the presence of infected cells, effector CD8 T cells are converted from naive CD8 T cells, and they proliferate according to interferon signaling, and their recruitment is inhibited by IL-6. Effector CD8 T cells cleared interferon from the system in this density-dependent form, and they die naturally at rate DE. After some delayed tau m days, memory cells are converted from effector T cells at the conversion rate zeta m. Upon reinfection or recurrent infection, memory cells transform into effector T cells when they recognize the antigen of the virus. And this conversion is regulated by the concentration of infected cells in this cell function form. We also consider the reconversion from effector T cells to memory cells. So this equation is the same as the previous one. The next step is to validate this model to data. Well, we use the mean input parameters from literature, and here this simulation compares the dynamics of these 12 biomarkers in primary and reinfection respectively. So our results indicate that in reinfection, the immune system responds faster, resulting in a mild COVID-19. For example, the maximum viral load and the maximum concentrations of infected cells are reduced in reinfection, and the immune system accelerates to eliminate virus and infected cells. Also, compared to the primary infection, effector CD8 T cells are generated without any delay, and they reach the peak very fast. This means in reinfection, the adaptive immune response is enhanced because memory CD8 T cell pool provides a rapid and effective resources for generating effectors. So this is the average case. We then next test the heterogeneous immunological memory response in the virtual patient cohort that we constructed in our previous study. So this is a framework of generating virtual patient cohort. We firstly create a parameter set, use the mean values and standard deviation from literature and clinical data. These parameters are related to macrophage, interferon, and IL-6 production. And then our model is simulated on these parameter sets. We used a simulated linear to make sure that the model trajectories fell within the ranges. That means to minimize this cost function. So we repeat this process until 200 patients are generated. By simulating our model in this virtual patient cohort, we get heterogeneous outcomes, but we are specifically interested in how differently the mild and severe patients respond in reinfection. So we need to find a way to define COVID-19 severity. Okay. Well, so we get some data from our hospital. These two plots show the concentration of IL-6 and CD8 T cell concentrations between mild and severe patients for alternating days. So we can see a clear separation for the IL-6 plot at day 5 and 6. So we use this biomarker to separate severe and mild patients in our virtual patient cohort. So, well, the severe and mild patient here are defined according to WHO index that is based on the level of ventilation. And here we also should know that severe patients tend to have lower CD8 T cell concentrations. Here are the simulation results in our virtual patient cohort. We used 40 of the IL-6 level at day 8 to separate mild and severe patients. So the red dots here identify the patients who are classified to be severe in a primary infection. Using this way of defining COVID-19 severity, our results indicate that there are fewer severe patients in reinfection, reducing from 94 to 36. We also plot the dynamics of other variables like CD8 T cells. So in primary infections, severe patients tend to have fewer CD8 T cells, but in reinfection, the CD8 T cell level of previously severe patients is diverse. We also look at the dynamics of other parameters and variables. We find that this cohort loses some heterogeneity in immune response because the values vary in narrow ranges. So, well, then we focus on our virtual cohort and try to find out which parameter determines severe COVID-19. So, well, firstly, we did a PCA test. This test can tell us, maybe I can skip it because it doesn't show any figure. Yeah. Well, yeah, PCA can tell us some correlation, but it can't tell us which parameter determines severe COVID-19. So we then did another test, that the homograph Smirnov test, for check the statistical difference in the distribution of their input parameters. So we find that these four parameters are significantly different, especially the first one, PM5L, for severe patients, is skewed to the right. And then we did a local sensitivity analysis for all these four parameters, and we find that the parameter PM5L, that is the differentiation rate from monocyte to macrophages. This rate determines the COVID-19 severity. In our virtual patient cohort, we find that a large proportion of patients changes from severe to mild in reinfection. So we then focused on this severe cohort and try to find which parameter reduce the inflammation. Similarly, we did a KS test for two groups. Better immunity means the patient who are severe in the primary but mild in reinfection. In addition, their IL-6 level decreased more than 15 places compared to the other patients in our cohort. And severe are the patients who are severely ill in both infections. We know that the first parameter is a determinant for severe COVID-19. So we then fix this parameter and run the local sensitivity analysis for the remaining three parameters. And we find that either high interferon production rate, high PFI, or lower monocyte recruitment rate will help the severe patients reduce the inflammation in reinfection. So overall, our study indicate that with CD8 immunological memory, patients can have stronger and rapid immune response in reinfection, but it can somehow cause a lot of heterogeneity in immune response. And also we identified the parameters that determines COVID-19 severity. That is a differentiation rate from monocyte to macrophage. And we also find two parameters, input parameters are very important for severe patients to get mild COVID-19 reinfection, that are production rate of type 1 interferon by infected cells and the recruitment rate of monocytes. And currently I'm working on another project to study the impact of the age on the humoral immune response after vaccination. So after that, I will construct a big model that combines both humoral and cellular immune response to get a comprehensive understanding of the immunological memory. Yeah, thanks all my lab members, all my colleagues and our collaborators. I really thank my supervisor, Morgan Craig. Yeah.
Well, so I will have time for a few questions, if any. Maybe I can start again. Yeah, just maybe two questions. I think it was in your slide, maybe 7 or something, when you got all those graphs with all the evolutions of different curves. Yeah, this one. So those were obtained by numerical simulations
Yes.
of your process with some given parameters, right?
Yeah,
Like
yes,
that.
yes.
Okay. And later on, so when you say you're going to generate some fake data, it was
So
yeah, exactly on that one. But on the very first one, so you say we draw parameters according to some normal distributions, but you don't have any correlations between parameters, or everything is independent for individuals. You don't have people with, I don't know, strong levels of something for all the components and.
Well, for now, I think we generated the independent parameters.
Yeah.
Those are not correlated. Maybe later. Yeah, but that will increase the complexity of the generation process.
Is it a common assumption to say that all the parameters should be independent? Because it seems very natural to say that they should be correlated.
Yeah, that's a good point. But it can be dependent. But yeah, we search for different literatures, and some literature only like do a research in a parameter. So yeah, I think that might be independent.
Okay. Any other comments or questions?
Can you go back to the model?
This one or
So how did you simulate the tau?
the top?
Tau, yeah.
So well, tau is a because this is a DDE, so tau m is a constant in our model. It only like shapes the curve to the right.
Does it affect the equilibrium points in that model, or does it affect the equilibrium point in that model?
Well, it's not it. So it won't affect the equilibrium point, but it only like some delay of the start. It's like the well, it's like the generation part is a little bit slow than the normal one. It won't, yeah, but the concentration won't change.
Okay. So if there are no more questions, thanks again. And we're going